video, we're going to discuss one algebraic approach to linear programming. So we've looked at linear programming via graphing. We know how to accomplish a linear programming problem using a graph, graphing our system of inequalities. Graphing is always kind of limited though, so if our problem doesn't have particularly nice numbers, graphing is sometimes an iffy approach to doing any type of problem, particularly if we don't have any type of electronic resources at our disposal. So algebraic techniques for solving problems are a little bit safer. However, sometimes they'll look a little bit more cumbersome than the graphing. We're just going to talk about an algebraic approach, and I'll try to relate it to how you graph as we go. So recall the model we looked at last section. We called it the tent problem. So we were talking about manufacturing tents subject to some constraints. So the goal was to maximize our profit, what we're thinking of as the output for producing these different products. So we had an objective function, P is 50 times x1 and 80 times x2, and we take the sum. So our first type of tent, we had $50 of profit from that type, and then we had $80 of profit from our second type of tent. This was the objective function of our linear programming problem. So we call it the objective function again because maximizing this function is the objective of the linear programming problem. So x1 and x2 in this case are our variables. The question is, how many type 1 tents do we need and how many type 2 tents do we need in order to maximize this function? However, remember, we're subject to some limitations on how much we can manufacture. If we can manufacture as much as we want, then the maximum of profit wouldn't exist. We could keep increasing our profit the more and more we manufactured. However, we know we can't manufacture indefinitely. We're limited based on our resources. So we had two problem constraints based on this manufacturing situation with these two types of tents. We had constraints in the cutting department and we had constraints in the assembly department. So we determined that there are a maximum of 32 hours in cutting and 84 hours in assembly, and we created two inequalities based on those limitations in those two departments. So all of this together forms our linear programming problem. We want to maximize this particular function, representative of profit, subject to these limitations. So the goal is to find the values that those variables can take on so that we can satisfy those inequalities and also find the highest value possible for profit. So this type of problem is called a standard maximization problem. We're trying to maximize our output. It's a standard maximization problem when the constraints involve less than or equal to inequalities. So notice the two problem constraints, both of the inequality symbols are going to be less than or equal to symbols. If we have constraints, regardless of how many, but the symbol we use is less than or equal to, then we fall under this category of standard maximization problems. Also, the number to the right of the inequality signs, all of those coefficients for our variables, for our decision variables, what we're trying to determine the values of, notice those are all positive. That's also going to be a factor that determines whether or not we have this standard maximization problem. Think of these as kind of ideal problems to solve. They're set up in such a way that we can solve them, and we can solve them in a pretty straightforward manner. So we're going to focus on problems of this type. So all of our problem constraints are of the form less than or equal to, and the coefficients for our decision variables are going to be positive numbers. Now again, we can solve with graphing, which is what we've done before, but graphing can be imprecise. We have pretty nice numbers here. All of our coefficients are whole numbers, but what if they weren't? What if they were fractional? What if they were irrational? There are a lot of possibilities for situations that don't look all that great, particularly if we're basing our problem on something from real life. Real life numbers typically don't cooperate all that well, in which case graphing may not be a good option because graphing is going to be limited in terms of how accurate we can be. What we're going to talk about in this video is what we call the table method for solving a linear programming problem. This is going to be one technique we can use if instead of graphing, we want to solve the situation algebraically. So maximizing the output, in this case the profit resulting from sales, based on the limitations we have for our decision variables. So the first thing we need to talk about in order to be able to use this, what we're calling the table method, is what we call a slack variable. So we're going to take the decision variables, x1 and x2, and we're going to add in some additional variables to our problem representative of what we're calling slack. So we're going to focus on the problem constraints for the time being. So keep in mind that problem constraints give information about the total amount of combined resources available for use. So the first problem constraint told us we have 32 hours to use in the cutting department. The first type of tent takes 1 hour. The second type of tent takes 2 hours in cutting. And so the combined time we spend on each of these activities is limited by that maximum of 32 hours. Now in the assembly department, we have a maximum of 84 hours. Tent 1 takes 3 hours, tent 2 takes 4 hours, and we know we can only manufacture up to those 84 hours we have in total. Now, so those constraints are representative of the total amount we have available and how those different values can be allotted to our different activities. What we're going to talk about with respect to this new type of variable is the fact that it's possible we can choose not to use everything available. It's possible that maybe we only use, 24 hours in cutting. Maybe we choose not to use all of the resources available. That may not be ideal, but we have to consider the possibility that that might be the case. Maybe we don't use all the resources available, even though we have a maximum of 32 and 84 hours in our two departments. So for example, suppose we produce 20 standard tents. Remember, those are represented by the variable x1, and then 5 expedition tents represented by the variable x2. What we want to know is how is this reflected in the problem constraint for cutting, which was our first constraint. Well, based on us making 20 standard tents and then 5 expedition tents, what does that look like in the cutting department? Well, we know it takes 1 hour to cut for a standard tent and 2 hours to cut for an expedition tent. So x1 is going to be 20. We've made 20 standard tents. x2 is going to be 5. We've made 5 expedition tents. So in terms of cutting, based on us requiring 1 hour and then 2 hours respectively, we end up using 30 hours in the cutting department. Notice that 30 still works in terms of this particular combination of manufacturing and values for our decision variables. All we know is that the amount of time we spend in that department has to be no more than 32 hours. Well, if we manufacture this number of each of these types of tents, we use 30 hours, which is less than or equal to 32. So this is a feasible combination for production. We could produce 20 standard tents and 5 expedition tents, at least based on what happens in the cutting department. What does that mean though? If we only use 30 hours, that means there are 2 hours that went unused, 2 hours in cutting that could have been used that weren't. These 2 hours are what we call slack. Slack is how much we have left over based on us not using all the resources available to us. So if we use 30 hours and have 2 left over, then we have 2 hours of slack. Now algebraically, we have to account for all of that. If we make 20 tenths of one type and 5 tenths of the other type and use 30 hours, we have to algebraically account for the fact that we didn't actually use all the way up to our maximum of 32. The additional variable we introduce is going to account for that leftover value. So slack variables are going to account for differences between the left hand and the right hand side of our inequalities based on the different values we might choose for our variables. So we're going to need 1 slack variable for every problem constraint. So in this particular problem, we have 2 constraints. We need a slack variable for inequality 1. We need a slack variable for inequality 2. Again, each of those variables are going to allow us to account for any type of resources we have left over that aren't used based on the values we end up solving for our decision variables. So we're going to use these additional variables to convert from what we call an I system. Think of I standing for inequalities. The constraints are written as inequalities. we're going to convert from an I system of inequalities to an E system of equations. So what does that mean? Well, if you think about taking the 20 standard tenths and the 5 expedition tenths, we know that sums up to 30 hours. If we were to then add on those 2 hours of slack, again, accounting for the fact that we didn't use them, but we know that they're there, we know that automatically we would be equal to 32. We would be equal to the maximum. So the 30 hours we used is certainly less than the 32, but if somehow we added in those 2 hours we didn't use, then we know we'd be exactly equal to 32. Say we came up with a combination where maybe we only used 26 hours. Well, we know there would be 6 hours of slack left over. So if we had a variable to account for that, we took the 26 we used, add on the 6 we didn't, it's automatically going to be exactly equal to 32, and we don't have to worry about the situation where it's less than. So those inequality signs are going to be converted to equal signs once we have that variable to represent that value that's left over in terms of our resources. So for the 10th problem, for the one we just did, again, we have 2 problem constraints, so we're going to need 2 slack variables. We're going to use the letter S to stand for slack, and we're going to use subscripts representing the first constraint and then the second constraint. So we're going to have these same components on the left-hand side as we already did. So x1, x2, those represent our decision variables. We know we have 1 hour for x1, 2 hours for x2. And then because of this issue with slack, this potential that we have to not use all our resources, we're going to add on that additional variable that represents how much we do not use. So if we were to take how much we do use and add on how much we don't use, we know the total has to be exactly 32. Now suppose we don't have anything left over and we use all our resources. Suppose we use all 32 hours. That just means the slack variable is going to take on the value of 0. If we use all our resources in manufacturing, then it's exactly equal to our maximum and we don't have any slack. So S1 would take on a value for 0. If, like in the situation we saw before, we only used 30 hours in terms of manufacturing the values that we had, then our S1 would take on a value of 2 in order to get the left-hand side and the right-hand side of the equation to balance. Now we have to do the same thing for the next constraint. So we have a maximum of 84 hours to use in the assembly department. 3x1 and 4x2 represents our actual usage. If for some reason we don't use all 84 hours and we have some slack, we have some hours and resources left over, S2 is going to account for those. So S2 because of the second constraint. So the subscript says this goes with the second problem constraint. Say for instance we only use 80 hours. Well, that means S2 would take on a value for 4 in order to get the left-hand side and the right-hand side of this equation to balance. So from this I system, we now have a corresponding E system. The same information comes from both versions of this problem, but we went from a set of inequalities to a set of equations. What we're doing is we're creating a system of equations. We have a lot of techniques we can use to algebraically solve a system of equations. So what we're doing is we're taking inequalities and we're converting them to corresponding equations so that we can then use some of these equation techniques that we know about. And let's do another one. So now we have an I system that has 3 problem constraints, 2 variables. Notice we have 2 decision variables, but we have 3 problem constraints. That means we're going to need a slack variable for each of the 3 constraints. So for the first constraint, we know we have to use less than or equal to 24 of whatever our resources are. If we use less than 24, then we have slack. So we introduce that slack variable to represent however much is left over. So if we take the amount we use and add on however much slack we have, it has to be exactly equal to 24. And then same thing for the second and for the third inequalities as well. So we have slack variable 2 for constraint 2 that represents how much we have left over from our total of 15 once we use however much we need to use. And then our third slack variable, sub 3, we take however much we use, we add on however much slack we have left over, whatever we don't use, and we know that the total has to be exactly equal to 24. So again, slack variables are just going to allow us to account for any resources that go unused. If we account for what we do use and what we don't use, then we know the total has to add up to be exactly the maximum available. So now we have our I system converted to an E system. How is that going to help us? Well, if you think back to the actual linear programming problem, now everything is an equation. So our objective function was already an equation. We didn't have an inequality involved there. It was an equation. If we take these inequalities and convert them to equations, now the whole problem is just modeled as a system of equations. So let's talk about how we would then go about solving. How do we know when we found a solution and what's that going to look like? So solutions that satisfy the I system, in other words, the inequalities, are going to be ordered pairs. So for our inequalities, we have two variables. Anything that satisfies the inequalities represents something that has a value for variable 1 and a value for variable 2. There's only two variables, so all the solutions are going to have two values. Now, the issue with solving inequalities or systems of inequalities based on what we've talked about is, remember, there's always a lot of values that we can have for our two different variables when we're talking about a system of inequalities. Graphically speaking, when we solve a system of inequalities, we typically have a whole region representative of solutions. So rather than have individual specific values for x1 and x2, we can have a lot of different values, and so we potentially have to make a list of a lot of different ordered pairs. So the ordered pairs that solve our system of inequalities can be expanded into solutions that satisfy our E system, our system of equations, as long as we know the values that these slack variables have to take on. So remember, to convert, we added in these additional variables that are going to represent however much we don't use. If we were to take ordered pairs and then add in a spot for each of the additional three variables, or in this case, two variables that we added on, then that's going to give us what would be a corresponding solution to the system of equations rather than the system of inequalities. Now, feasible solutions, solutions that can actually work in the situation, that actually represent possible solutions to the applied problem, are going to be those in which all various variables are positively valued. In other words, we don't have any negative values. If we're talking about something like a manufacturing situation, manufacturing a number of items, we can't manufacture a negative number of items. We also can't have negative slack. What would negative slack mean? In order for slack to be negative, so say for instance with the tent problem, say our slack was negative, that means that was the number that was needed to balance the left-hand and right-hand sides of the equations. If slack was negative, then that means how much we used was actually bigger than 32. It means we used too much. It means to get the left and the right to balance, we needed a negative number. We needed to deduct from our total. So having any negative values, if the decision variables were negative, it means we manufactured a negative number of items, which just doesn't make sense. If our slack variables are negative, it means we overused our resources. We used more than 32 hours, and so we had to account by deducting at some point. So actual solutions that represent possible combinations that could solve our problem are going to be ones where all of the variables take on non-negative values. Some of them can be 0, that's fine, but we can't have any that are negative. So for example, consider the tent problem. We have given values of x1 and x2. We want to use these to find a solution to the E system, the actual system of equations, not the system of inequalities, and then we'll determine whether or not each possible solution is feasible. So for the first combination, x1 is 20 and x2 is 5. So that's actually the combination we were given on the previous page. Remember when we were asked to determine what happens if we make 20 tents and then 5 expedition tents? That was the situation we were in before. So remember, with the first constraint, we determined we had 2 hours left over. We had 2 hours of slack. So that would be reflected in the E system in our slack variable. So we just want to finish this out and take it one step further. In other words, big picture, what happens if we manufacture 20 standard tenths and 5 expedition tenths? Now I'm looking at my system of equations though. So this was the E system. This is what we got when we converted the inequalities for the tenth problem to equations that now had slack variables. So what we've been given are different combinations for actual manufacturing. We've been told we made 20 standard tenths and we made 5 expedition tenths. We want to determine what would the whole solution look like. In other words, we know values for x1 and x2, but those other 2 variables that we now have, what values would those have to take on in order to represent the whole situation and all 4 variables? So I'm going to take my 2 equations and I need to sub in the values that I know. So for equation 1, we have x1 plus 2x2 plus s1, our new variable, our slack variable, is equal to 32. So I know x1, I know it's 20. I know x2 is 5. So I'm going to sub in those values that I do know. And now I have to determine what would the value be for s1 in order to make this equation true. So 20 plus 2 times 5 is going to give us 30. So 30 plus S1 is going to be exactly equal to 32, which means S1 has to be 2. Remember, that's exactly what we said on the previous page. We said that the slack was going to be 2 hours. So in this case, the variable representing slack takes on the value for 2. So what this is saying at this moment is that if we use 30 hours, then the amount of slack left over is going to be 2 hours. So that means if x1 and x2 are 20 and 5 respectively, then the amount of slack for constraint 1 is going to be exactly 2. Now we need to do the same thing for the second equation, the one we haven't looked at yet. So 3 times x1 plus 4 times x2 plus s2, slack variable 2, the one for the second constraint, all of that has to sum to exactly 84. So however much we use plus however much we don't use has to sum to exactly 84. So again, I'm going to sub in the values of 20 and 5 for the 2 decision variables. So we have 3 times 20, which is 60, plus 4 times 5, which is 20. 60 plus 20 is going to give me 80. So 80 plus slack variable 2, the amount left over in the assembly department for the assembly related constraint, has to be exactly equal to 84. So if that's the case, then slack variable 2 is going to be 4. I subtract 80, move it over, slack variable 2 is going to be 4. So what that means is if we manufacture 20 standard tenths, 5 expedition tenths, we have 2 hours left over in the cutting department represented by constraint 1, and we have 4 hours left over in the assembly department represented by constraint 2. So our actual solution is going to take these 2 values, which would have just been an ordered pair if we only had 2 variables in the problem. But we're going to take that ordered pair and then we're going to expand it to include the values for S1 and the value for S2. So S1 is going to be 2, S2 is going to be 4. So we have an ordered quadruple, I guess is what we would call it. So 20 and 5, which we were given, and then slack variable 1 is a value of 2, slack variable 2 is a value of 4. So this would be the solution to the E system, which has 4 different variables represented. This is a feasible solution because all of the variables take on positive values. As long as the decision variables are positive and the slack variables are positive, we know this is feasible. In other words, if we were to put this into the context of the actual problem, this is a possible combination that could represent a real choice in terms of our manufacturing decision. Now let's look at another one. So suppose instead we pick x1 to be 20, so we don't change that. But now we're choosing x2 to be 8. So before we determined that it was going to be 5, we were going to manufacture 5 expedition tents. Now we want to manufacture 8, and we want to see what would the whole solution have to look like in order to manufacture 20 standard tents and 8 expedition tents. So same idea, we're going to take our E system, so our constraints in equation form. We're going to sub in the values that we know, in other words, the proposed values for our decision variables, and then we're going to solve for the values for these slack variables. So x1 is 20 plus 2 times x2, which is 8. So there's our constraint for the cutting department. And then plus our slack variable, representative of whatever we don't use. And we know that all of that has to sum to 32. So 20 plus 2 times 8, which is 16, is going to give us 36. So 36 plus S1 is equal to 32. I'm going to subtract the 36 to move it over. So we know that S1 has to be -4. So in order to manufacture 20 regular tents and 8 updated tents, slack has to be -4, okay? Well, think of that as negative hours. Does that really make sense? Probably not. But let's keep going. Let's solve the other one as well. So now the constraint for the assembly department. 3 times the 20 standard tents plus 4 times the 8 expedition tents plus our slack has to come out to exactly 84. So 3 times 20 is going to be 60. 4 times 8 is going to be 32. 60 plus 32 is going to be 92. So 92 plus our slack is going to be exactly equal to 84. Again, I'm going to take my 92, subtract it, move it over, which isolates our slack variable. So this slack variable is going to be -8, which again means now we're talking about hours. That's the variable representing the leftover resources, the leftover hours. Well, we have -4 hours and -8 hours, which means technically we've overused our resources. We've used more hours than we actually have available. So if we take the ordered pair represented by our decision variables and add on the values of our 2 slack variables, now we have that possible solution. However, we know that this potential solution is not feasible. The fact that the slack is now negative again means we overused. So we used 36 hours in cutting, whereas we only had 32 available. We used 92 hours in assembly, whereas we only had 84 available. So this is not going to be a possible combination that could work for us. It's not a feasible solution. So based on what we now know about graphing, think about it again from the graphing standpoint. Let's put this all together. All the feasible solutions. So this is a possible feasible solution. 20 and 5 with 2 and 4 left over as slack. That's a feasible solution. 20 and 8 is not a feasible solution because we have negative slack. All the possible solutions, the feasible solutions, exist within that solution region that we found through graphing. So when we graphed those inequalities and looked for the locations where they overlap, the solutions are represented in those locations where the inequality graphs overlap. And we know based on how we did the linear programming from there that all of the optimal solutions we're going to find are going to come from the corner points. So if we look at that solution region, it's defined as a bunch of line segments. It's one region bounded by some line segments, and those line segments join at corners. So the corners represent the possible locations where we could have our optimal solution, where in this case we could maximize our profit. What we want to do now is rather than graphing, we want to determine what would those corner points look like if we don't have inequalities anymore. So everything we know from talking about graphing is still true. The actual solution, the optimal solution, the solution we want is still going to occur at one of those values that we get from a corner point. But if we don't have a graph, well, how do we know where the corner points are? What we're going to do is we're going to artificially generate all of those corner points using an algebraic technique. So we're going to generate the possible solutions. In other words, the corner points. Those are the possible solutions. We're going to generate those by taking the E system, taking the system that has those additional slack variables, and we're going to find all combinations of variables where two of the variables take on a value of 0. What this is doing algebraically is it's generating the locations where the equations in the E system would intersect. In other words, if we were to graph them as actual equations, in other words, they generate lines, those particular values where we let two variables be equal to 0, those represent locations where our equations, where their lines would intersect. In other words, where we form corner points. So by assigning two variables at a time to take on a value of 0, we're going to artificially generate those locations where we get a corner point from graphing. We're going to then use that, we're going to take it one step further, and we'll essentially do things the same way we did when we graphed. We looked at the corner points, we took those corner points, plugged them into our objective function, and we looked for the maximum or we looked for the minimum depending on the situation we're in. So let's summarize what we're going to call the table method. So we take our I system, convert it to an E system, exactly what we did before. Now we're going to assume that standard maximization problem. We assume we have two decision variables and two problem constraints. We're going to start out simple. So take our I system, what we graphed the last video when we looked at linear programming with graphing. We're going to take that I system, we're going to convert it to an E system. In other words, take all those problem constraints, add in the slack variables, one for each of those constraints, and then convert from inequalities to equations. So we're going to then form a table with each variable, the decision variables, the slack variables. We're going to have a column for each of those individual variables. We're going to then fill in all the rows of the table with all the possible combinations where we could assign two of the variables a value of 0. This is going to take a little bit of work to make sure we cover all the possibilities, but we have to look at all the possibilities where we assign one value to 0 and another value to 0, and then solve for the remaining variables that aren't assigned a value for 0. So what we're going to end up with is a system of equations. So for each row, we have a small system of equations. We're going to solve that system if possible. We're not going to complete the system when there are 0 solutions, in other words, no solution, or infinitely many solutions. Those situations aren't going to pop up very often, but if they do, then we know that that particular row doesn't represent a possible solution to the linear programming problem, so we're not going to worry about that particular row. So each row gives what we call a basic solution. It's one of the possible solutions that we could base our linear programming on, and we could base our decision making on. And then the rows with non-negative values, where all the values are either 0 or positive numbers, those are going to be the ones where we have basic feasible solutions, the ones that we can actually consider as possibilities for solving the applied problem. So we're going to categorize each row after we solve for the remaining values as either feasible or not feasible. We're then going to take the feasible rows, the ones that represent possible solutions, and we're going to use those to solve the linear programming problem. So we're going to find the maximum value of our objective function for each of the feasible solutions based on the ones that don't have any negative values, based on the ones that have feasible solutions. Whichever combination of values maximizes our objective function, we know that's going to be the solution to our linear programming problem. So again, just to recap, we're going to take the I system, convert it to an E system. We're going to set up a table where all the columns are representative of our variables, the decision variables, in other words, the X's, and then the slack variables, the S's, the new variables. We're going to come up with all the different combinations where two variables could take on a value of 0. Each of those different combinations is going to give us a system where we have to solve for remaining variables. Once we solve all of the rows, determine all the combinations based on values of 0 and values that are not 0, the feasible solutions are going to be rows where none of the values are negative. The non-feasible solutions occur when we have potential values that are negative. we're then going to check the objective function using those feasible rows, the combinations that don't have any negative values, and we're just looking for the maximum. So based on the feasible solutions, where is the objective function going to take on a maximum value? So let's look at an example. Okay, so first thing we want to do, we want to use slack variables to convert our I system to an E system. And then we want to find just some individual basic solutions. So we're going to start out small. We're not going to do the whole problem. We're just going to start out small. So convert to an E system, and then check a couple different combinations, determine what the solution would be in total, determine whether or not that combination would be feasible for solving a linear programming problem. Okay, so our I system is going to be 3x1 plus 2x2 is less than or equal to 21. And then x1 plus 5x2 is less than or equal to 20. I'm going to take this I system and convert to an E system by adding in a slack variable for each constraint, and then taking my inequality sign and converting it to an equal sign to create equations, an E system instead of an I system. So for the first constraint, I'm going to add in S1, slack variable for constraint 1. So we have 3x1 plus 2x2 plus slack variable 1 is now exactly equal to 21. So the amount we use plus our leftovers are exactly equal to 21. Same thing for the second constraint. So x1 plus 5x2 plus the slack variable for constraint 2 is going to be exactly equal to 20. So the resources I use plus my leftovers are going to be exactly equal to 20. So these are now going to be the versions of the constraints that model this situation. So we have our E system. We now want to determine what would the whole solution, in other words, to find the value for x1, x2, and then the two slack variables. What would the whole solution look like based on some specific values for specific variables? So the first combination we want to check is the combination where x1 would be 0, and then slack variable 1 would also be 0. So I'm going to substitute those values into my two equations, and then I'm going to go from there. I'm going to start with the first equation. How do I know where to start? Because this is a system of equations and I can really start with either. Think about what's going to be easiest to plug in. So I've given x1 and s1. The one equation that has both of those variables is going to be equation 1. There's your x1, there's your s1. Equation 2 only has one of those variables. So we want to start by substituting into the equation that has more of the variables available to us. So I'm going to take that first equation and I'm going to substitute in 0 for our x1 and 0 for our slack variable as well. So those first and third terms are going to cancel because they now are identically 0. So that leaves us with the middle term, which only has the variable x2 in it. What that now tells me is based on this substitution, the first variable I can solve for is going to be the second decision variable. So I'm going to solve for x2 by isolating x2, divide 2 from both sides. So we get that x2 is equal to 21.2, or 21 divided by 2, excuse me. If we wanted to convert that to a decimal, we could, of course, divide at that point. Just depending on the situation we're in, we can either convert to a decimal or leave it as a fraction. General rule of thumb is unless you're told that you can convert to decimals, you should leave things as fractions. So we now actually have 3 out of our 4 values. We know x1 and s1 because they were given. Now we know the value for x2. So all that's left is to find the value for our second slack variable. So I'm going to take what I know. I'm now going to go to the second equation. So x1 was given, and then we just solved for x2, which now leaves that third slack variable that we need to solve for. So x1 was 0. That cancels out, leaving us just with the remaining 2 terms. I'm going to sub in the value that I determined for x2, which was 21 over 2. Plus our slack variable is equal to 20. So now notice we have 2 constants, we only have 1 variable. Now if you don't like to deal with the fractions here, this is a great time to use your graphing calculator to help you handle the issues with the fractions. So I have 5 times my value for x2. So I'm going to take those 2 and I'm going to multiply them together. So 5 times 21 over 2. Okay, so that's now going to be the value in front of S2. Notice it's a decimal right now. We'll convert back to a fraction at the end, so you don't need to do anything with that right now. So that's now the number that's added on to S2. If I want to solve for S2, I need to subtract that and move it over to the other side of the equation. So I'm subtracting it from 20. So I'm going to take 20 and then I'm subtracting that number. So 20 minus 52.5. And that's not what I want. Let's see, that's a decimal. There we go, 52.5. And that's going to give us negative 32.5. Now, if we want that as a fraction, remember your calculator can handle that. You're going to go to the math menu and option 1, arrow frac, convert to a fraction, and then it's going to convert it to a fraction for you. So negative 65 over 2. So don't be alarmed if you run into fractions. If you're uncomfortable with fractions, use your graphing calculator, work with the decimals as far as you can. Make sure you don't round anything anywhere, but work with the decimals in your calculator, and then at the very end, just convert your answer back to a fraction. That's perfectly fine. So that is going to be the value that S2 has to take on in order to fit the combination of values that was given and that was solved for. So our solution, our basic solution, based on these given values for x1 and s1, is going to include an x2 value of 21 over 2. So x1 is 0, x2 is 21 over 2. S1 was given as 0, so the next coordinate is going to be 0. And then the last coordinate, S2, that we solved for, is going to be negative 65 over 2. So then the question is that solution feasible? Is that a possible solution that solves the linear programming problem associated with these constraints? We know this is not feasible because of that last slack variable. As soon as that slack variable is negative, that means we've overused our resources. So although slack variable 1 is okay, we don't have any slack for variable 1, we do have negative slack for the second problem constraint, which means this is not a feasible solution. It is a basic solution in the sense that it represents a corner point. If we allow 2 of our values to be 0, then we generate what we can think of as a corner point. But because that substitution results in negative slack, it means this is not a potential combination that could solve a linear programming problem, so it's not feasible. Now let's try another one. So now we have that S1 is 0 and S2 is 0. In other words, we're letting both of our slack variables be 0. What that means from a practical standpoint is that we're using all of our resources and we're letting the slack be 0. So if slack is 0, it just means we're using up all 21 and all 20 of our 2 respective resources, be they hours or actual physical resources. So same idea as before. I'm going to substitute these values into my equations, and then I'm going to go from there and solve for whatever's left over. Now, based on what we were given, these 2 variables can only each be substituted into one equation. So only one equation contains S1 and only one equation contains S2. S1 corresponds to the first constraint, and then S2 corresponds to the second constraint. So I can only substitute each of those values into one of the equations. What that means is going to be a little more complicated to solve for the remaining values than it was before. It was pretty direct to solve before because we had one equation where we were able to quickly isolate a variable, and then we just went from there. This is going to be a little bit different. So I'm going to take my 2 equations, sub in my slack variables. I have slack variable values of 0, which essentially just means those 2 terms go away. What results is now 2 equations with 2 variables, and they're each the same variable. Now we have essentially a 2x2 system of equations, 2 equations, 2 variables. We have a lot of techniques we can use to solve a system of equations like this. So for instance, I'm looking at equation 2. I notice there's x1 without a coefficient. I could isolate x1 by moving this term over, by subtracting it, and then I could take that expression and replace x1 in the other equation. In other words, I could use substitution if I wanted to solve. That would be a fairly straightforward way to solve that system. Also, if I were to take this equation and multiply it by -3, we would now have 3x1 here negative 3x1 here, I could add those two equations together, and that would also allow me to solve. So that's another option as well. A third option would be to write an augmented matrix and solve this using an augmented matrix, which is what I've done here. So my first equation is going to be my first row in the matrix. So notice S1 is no longer there. It's now just X1 and X2. So that's going to be the first row. I'm going to write in the coefficients and then write the constant on the other side of my vertical line. And then my second equation is going to be my second row. Now keep in mind that X1 has a coefficient of 1, so I'm going to write a 1 right there. So let's review how we go through and solve that since it's been a little while. Make sure my matrix menu is set up. I'm going to clear out my memory. Give me just a second. Let's see. Okay, just as a reminder, how do you clear out your memory if you want to get rid of matrices and only matrices? Right above plus, where it says mem, that stands for memory. So second and plus takes you into the memory menu. You're going to go to memory management and delete, which is option 2. Hit enter. And then I only want to deal with matrices right now, which is going to be option 5. So I'm going to scroll down to option 5, hit enter. And then each of those two matrices we've typed in, I want to get rid of those. So I'm going to delete the first one, delete the second one. And now that means once I go into the matrix menu, it's going to be clear and I can start from scratch. You certainly don't have to do that, but if you're like me and you don't like seeing that menu full when you go in there, you might want to clear your matrices from time to time and then start back over. So the matrix menu is attached to the inverse button, x to the negative 1 in blue. So second, x to the negative 1 takes me into my matrix menu. So remember, we go right to left. Edit is where you enter a matrix. Math is where you find any operations you want to use. And then names is where you find matrices you've already typed in. So we're going to go edit, math, and then names. So I'm going to go to the edit menu. I'm just going to highlight and enter into the first matrix. So I need to enter my dimensions. It's rows by columns. So this is going to be 2 by 3. And then I'm going to type across the row and then down to the next row. So 3, enter, 2, enter, 21, enter, 1, enter, 5, enter, 20, enter. And of course, after you type it in, before you do anything else, double check that you typed what you intended to type. If there's a typo, that's going to propagate through the rest of the problem. So double check now that you typed what you intended to type. So this looks good. Now remember, you can't clear to get out, you've got to quit to get out. So second and mode will take you out of there. And now your calculator has that matrix typed in, saved as matrix A. You're going to go back into the matrix menu. So second, x to the negative 1. We've used edit. Now we're going to go to math. And notice we now have that matrix saved right there. We'll get to this last. So go to the math menu. What we want to do is reduce this matrix and put it in what we call reduced row echelon form. In other words, put it in a form where we can immediately read off the solution to this system of equations. So I'm going to scroll down until I find RREF, which is going to be option B. I'm going to highlight that, hit enter, puts it on my home row. And then I'm going to go back into the matrix menu one final time, and I'm going to highlight the matrix I want to use under the names submenu, and then hit enter. And so this says we're taking the reduced row echelon form of this matrix called A. And I'm going to hit enter, and then it reduces. So the left-hand square of the matrix now represents the coefficients for our variables in those two equations, and the right-hand side represents the actual values. So this is my reduced form. I have it written down. Equation 1 now represents 1x1 and no x2s. So in other words, x1 isolated by itself. So we know x1 is going to be 5, and then no x1s but 1x2. So x2 is going to be 3. So those are going to be the two remaining values. So whenever S1 is 0 and S2 is 0, the corresponding values for the decision variables are going to be 5 and 3 respectively. So the solution to the E system, which requires 4 values, is going to be x1 is 5, x2 is 3, and then the two given values for the slack variables are 0. Now we know this is a feasible solution because all the values are non-negative. The lowest values we get are 0. It's possible for variables to take on a value for 0, and then the decision variables have values of 5 and 3. Now that does not necessarily mean that in the context of a linear programming problem, this is going to be the optimal solution. It doesn't necessarily mean that. All it means is that this particular combination represents a corner point. If we were to graph these inequalities, this represents a corner point, so it represents a possible combination that could result in the optimal solution. So imagine taking each of these individual steps. Here we substituted for x1 and s1. Here we substituted for s1 and s2. If we were to put all of this into the context of one big problem, we have to do these substitutions with every combination of variables. So we just did the combination for x1 and s1, and then for s1 and s2. Well, we'd also need to know what happens if x1 and x2 are 0, and x1 and s2 are 0. All the different ways we could combine two zeros into our problem. So what we're going to do now is we're going to put it all together. We're going to go start to finish. So take the inequalities, add in those slack variables, convert them to an E system, determine all the different ways to pick two values to be set to 0, solve for the resulting values, and then use the results of there to find the maximum for our objective function. So let's look at an example. Okay, so we want to construct the table of basic solutions for this linear programming problem, and we want to use it to solve just based on the values that we get. Okay, so here's our problem. We want to maximize P is equal to 15x1 plus 20x2, subject to these problem constraints. So x1 plus x2 has to be less than or equal to 6, and then x1 plus 4x2 has to be less than or equal to 12. So we have a standard maximization problem, so we know we can use the table method. I'm going to start by converting my inequalities to equations using the slack variables. So we have two inequalities. We need two slack variables. So slack variable 1 for the first constraint, the less than or equal to becomes an equal to. So the resources we use plus the slack, the leftovers, is going to be exactly equal to 6. And then the same thing for the second one. So x1 plus 4x2 plus slack variable 2 is equal to 12. So the amount of resources we use plus the leftovers are going to be exactly equal to 12. So that's going to be our E system. Okay, so notice we now have 4 variables. We have 2 decision variables, x1 and x2. Those represent the actual values that we want to determine to maximize our profit. And then we have our slack variables, s1 and s2. So in total, we have 4 variables that we have to solve for in any situation. So my table has a column for each of those variables. And then the last column, I've put the objective function. We're going to determine the combinations for the variables, and then based on those combinations, we want to determine the value for the objective function. What we're looking for is which combination is going to maximize that objective function. So the table's filled in right now, which is misleading, but what we need to do first, imagine this table is completely blank, the grid is completely empty. We have to determine all the different combinations of assigning 2 variables a value of 0. So the way I like to do it is just start with a 0 in the x1 column. So 0 here, and then pick another variable to be 0. So the first combination would allow x2 to be 0. So 0 and 0. Well, now we need the combination where we keep a 0 in x1, but we move the next 0. So it would move to s1. And then the final combination there would have x1 is 0, and then move the 0 to x2. So those would be all the different combinations where x1 has a value of 0, and then another variable has a value of 0. Well, now we need to move over. So now x2 has a value for 0, and then s1 has a value for 0. So that's another combination we haven't seen. x2 could be 0, and then s2 could be 0. So think of moving the zeros each time. Here's the first 0, and then a diagonal. Now move that first 0, and then a diagonal. And then finally, the last combination would be s1 is 0 and s2 is 0. What we then need to determine is in each of those situations, what are the remaining values in order to allow those particular zeros to exist. So we have 6 different little mini problems inside of the big problem that we have to solve. So we're going to go solution by solution to determine what are the combinations. We'll determine which ones are feasible, which are not, and then we'll determine where the maximum is for our objective function. So let's start with solution A. So solution A, we're allowing x1 and x2 to both be 0. So I'm going to substitute those values into my E system. Now notice these 2 values exist in both equations. So this is going to be a really quick one to solve. I'm going to take both equations and substitute 0 in place of those 2 decision variables. So for the first equation, all we then have is S1. S1 is isolated. So S1 is going to be equal to 6. I'm going to substitute those values into the second equation. Again, the first 2 terms are going to reduce to 0, which means I now only have S2, and S2 is equal to 12. So that's going to be 12. So 6 and 12 are going to be the values of the remaining 2 variables based on those assignments of 0. This is going to be a feasible solution because we don't have any negative values. Because all these values are non-negative, this is a feasible solution. So this will be a solution that we'll check once we get down to the maximization part of the problem. Now we need to keep going and we need to do the same thing for each additional combination. So now I'm going to look at B. So we're allowing x1 to be 0 and we're allowing s1 to be 0. So I'm going to make those substitutions. I'm going to start with the equation that has both of these variables. So equation 1 has both an x1 and an s1. I'm going to start by substituting there. So x1 is 0 and s1 is 0, which just leaves x2 in that particular equation. So we get that x2 is equal to 6. So I can go ahead and put that into the table if I want. Now I need to substitute in the other equation to solve for the remaining variable. So I'm going to substitute in x1, which was given, x2, which I just solved for, and then s2 is now my unknown. So I have 24 plus s2 is equal to 12. I'm going to subtract that 24, move it over. So S2 is equal to negative 12. So that's going to be the last value for that particular solution. Now this is not a feasible solution because we have a negative value. Negative slack, again, means we've overused our resources. So this is not a combination of values that would actually work for this linear programming problem because, again, that negative slack means we've overused our resources. So I'm going to mark that as a non-feasible solution. We won't actually have to check that one because this is not a combination that could exist in real life. Okay, let's go and check solution C. So for solution C, we're letting x1 be 0. We're letting s2 be 0. And you may want to make a note of the equations as you go. So I'll flip them back over one more time. Here are our equations for our E system. Or maybe I can just slide as we go. That'll work. I'll slide things as we go. Okay, so we're substituting for x1 and for s2. Now, there is another equation that has both of these, just like with the previous solution. So notice the second equation has both an x1 and an s2. So I'm going to start with that equation, substitute where it's going to be easiest to solve. So x1 is going to be 0, s2 is going to be 0, and I'm just left with that term in the middle, 4x2. So I have 4x2 is equal to 12. I'm going to divide by 4 so that we get that x2 is going to be 3. So x2 is going to be 3. Now I'm going to take everything and substitute into the first equation, the one I haven't used. So x1 was given to be 0. We determined that x2 was 3. And now we're solving for slack variable 1. So 3 plus s1 is going to be 6. I'm going to subtract 3, move that over. So S1 is going to be 3. So X2 is 3, and then S1 is going to be 3 as well. This is going to be a feasible solution because all the values are non-negative, so this will be one of the solutions we check in our objective function. Okay, let's look at the next one. Now we're allowing X2 to be 0 and S1 to be 0, which means we're solving for X1 and S2. again, I'm going to start with the equation that has both of these variables. So equation 1 has both an x2 and an s1. So I'm going to start with that equation. I'm going to sub in 0 for each of the given variables. So we have x1 plus those two zeros is equal to 6. So we know x1 has to be 6. So x1 is going to be 6. Now I'm going to substitute into the second equation, the one I haven't used. So x1, sub in the 6 we just found. And then x2 was given to be 0. And then we have s2. Now notice it's 4 times 0, so that comes out to 0, but then s2. This wasn't written very well. But then we have s2. So 6 plus s2 is going to be 12. I'm going to subtract that 6 from both sides. So we get s2 is going to be 6. So there's that additional value. This one, solution D, is going to be a feasible solution. All the values are non-negative. So we'll have to check this one in our objective function. Okay, now let's look at E. So for E, we have x2 is 0 and s2 is 0. The equation that has both of these values is going to be equation 2. So I'm going to substitute in there. So x1 plus 4 times 0 plus the slack value of 0. So those two terms are eliminated. So we have x1 is equal to 12. So x1 is equal to 12. Okay, I'm going to take that value, take what I know, and substitute into the remaining equation, that first equation. So x1 is going to be 12. We were given that x2 is 0, and then the remaining variable is going to be s1. So 12 plus s1 is 6. Subtract the 12, move it over. So s1 is going to be negative 6. So that's our remaining value. This solution, also not a feasible solution because we have a negative value for slack. So again, that means that we've overused our resources. This is not a possible combination that could solve our problem. Now let's look at the last one, and I'll flip this back over. We're subbing in 0 in place of both of our slack variables. So we end up with x1 plus x2. The slack variable is eliminated, so that's going to be exactly equal to 6. And then x1 plus 4x2 plus 0 is equal to 12. What this particular combination represents is the situation where we don't have any slack, where we use all our resources. Conceptually speaking, it makes sense that you would probably optimize any situation by not having slack. That's not always the case though. So we can't automatically assume that by using everything, we end up with the best outcome. Maybe by using everything, our cost ends up being higher than it could be in another situation, so our profit isn't optimized. So we can't make that official decision without actually checking the values in our objective function. Now this one is automatically the most challenging one to solve, just because I can't eliminate a variable combination in such a way that we can just immediately solve for one of the remaining variables. I now have a system of 2 equations with 2 variables. So I chose to use a matrix again. And remember, you could do substitution, maybe solve for one of these variables and then sub into the other equation. You could do elimination, so maybe multiply one of these by a negative and then combine and eliminate those x1s. That's an option as well. I just used a matrix. So first line would be 1, 1, and 6 for the first equation. And then the second line would be 1, 4, and 12 for the second equation. I reduced this in my calculator, and this is the reduced matrix. So we know that x1 has to be 4 and x2 has to be 2. I'd recommend if you want to use a matrix, maybe pause the video for a minute. Make sure you can put this matrix into your calculator and you can reduce it and get the values you're supposed to get. So those are going to be the last combinations of values. Okay, so x1 is 4 and x2 is 2 whenever our slack variables take on a value for 0. So essentially what we've done here is we've generated all the corner points plus some. So keep in mind, if we were to graph the inequalities, we don't actually have the variables s1 and s2. We only have the variables x1 and s2 and x2. So this is a little bit bigger than the corner point table would actually be if we graphed this system. But this is going to give us all the information we need plus some. So disregarding the non-feasible solutions, which again we categorized based on there being negative values, we're going to take the remaining solutions be feasible solutions. These are basic feasible solutions, basic in the sense that we could base our problem on those, and feasible based on the fact that they are possible solutions that could actually work in real life. I'm going to substitute into my objective function. Now this is going to look a little strange because notice these two variables, x1 and x2, those are the only variables in that objective function. So although our E system has 4 variables, we only actually have 2 variables to substitute for in this objective function. So in those situations where we could sub in a non-zero value for S1 and S2, keep in mind we can't actually sub those into the objective function. That actually makes sense though. If you think about what the profit function represents, we're making profit off of selling one type of item and another type of item. We don't make profit off of slack. Slack is just a number representative of leftover resources. Well, we're not making any profit off of leftover resources. The only thing that contributes to our profit is what we're actually producing and selling. That's representative of those decision variables. So just be aware, in some locations you will be plugging in 0 even though the slack variables have taken on non-zero values. So for combination 1, x1 has a value of 0 and then x2 also has a value of 0. So not surprising, our profit comes out to 0. In other words, if we make and sell nothing, then we don't make any money. So not surprising. Now the next feasible combination, we make none of the first type of item, we make 3 of the second type of item, and then we have 3 elements of slack left over from the first problem constraint. So I'm going to plug in 0 for x1 and then 3 for x2. So the first term reduces to 0, so we have 20 times 3, which is 60. So in this case, our profit is going to be $60, whatever we're looking at. Okay, the next feasible combination would be x1 is 6 and s2 is 6. Now this value, even though this is non-zero, there's nowhere to plug in this number into our profit function. The only things we're plugging in are going to be the values for the decision variables, which in this case are 6 and 0. So 15 times 6, 20 times 0. So this term is eliminated, and we just have 15 times 6, which is going to be 90. So far this is the optimal situation. We started with no profit, and then $60, and then $90. So we continue to improve. Solution E was not feasible because of that negative slack. And then solution F is our last combination. So now we're letting x1 be 4, x2 be 2, and we have no slack left over. So we're not using up any slack in any situation. We're using all our resources available to us with no leftovers. So we have 15 times 4, and then 20 times 2. So 15 times 4 is going to give us 60. 20 times 2 is going to give us 40. 60 plus 40 is going to be 100. So because that is going to be the highest value that results from a combination of feasible values in our table, that's going to be the optimal solution to our problem. So we know the maximum value for our objective function is going to be 100. In this case, maybe think of it as $100. And it occurs when x1 is 4 and then x2 is 2, and we allow the slack variables to both take on values of 0. Now again, this does seem to make sense because this means we're not using any slack. It means we don't have anything left over. We're using all our resources in manufacturing item 1 and in manufacturing item 2. This will not occur in every situation though. In some situations, the slack is a good thing. If we don't make enough profit off of something to account for the cost, then in some situations, leaving a little bit left over may actually lead us to a better outcome in terms of sales, revenue, profit, something like that. Okay, so that's in general what these kind of problems are going to look like. It's tedious. I completely see that it's tedious, but it's very formulaic. So once you have your E system, draw your table, write in all the different combinations of zeros, solve the system of equations for each combination. Notice with each of those little systems, with the exception of the very last one, The individual systems were actually pretty quick to solve. So except for the very last one, you could immediately solve for at least one of the variables, and then max you had to do maybe one additional substitution and then solve for the last variable. So usually those individual solution systems that you have to solve are going to be pretty straightforward. They're not going to take a while. You just have to be organized. You have to be methodical. Okay. So let's talk about one last concept and then we'll be done. Basic versus non-basic variables. Categorizing our variables based on the different situations we end up in. In other words, basic versus non-basic means what are we basing our solution on and what are we not basing our solution on. So consider a basic solution, in other words, one of the ones we get from the table of this form. Here's our decision variables. Here's our slack variables for our two problem constraints. The non-basic variables are those that are assigned a value for 0. If they're assigned a value for 0, they're not contributing anything to our solution. They're not contributing anything to the maximization of our objective function, so we're not basing our solution on them. The basic variables are those that are not assigned a value for 0. If they're non-zero, then that means somehow they're contributing to our objective function, which means they're something we base our solution on. So we've got a table of 6 basic solutions for our E system. For each solution, we just want to identify which variables are basic and which variables are non-basic. So first solution, we allowed x1 and x2 to be 0. So s1 and s2 are the non-zero values. So for that solution, the basic variables are going to be s1 and s2 because those are the ones that have non-zero values. The non-basic solutions, or not solutions, variables, the non-basic variables are going to be x1 and x2 because those have taken on a value for 0. So if we were to follow solution A, we're basing our solution on S1 and S2, and we're not basing our solution on X1 and X2. For solution B, the basic variables are going to be X2 and S2. The non-basic variables are X1 and S1. For solution C, the basic variables are going to be X2 and S1. Now notice S1 is negative, which means this is not a feasible solution. But if we're just categorizing basic versus non-basic, X2 and S1 are basic, and then X1 and S2 are non-basic. For solution D, X1, S2, those are basic, X2 and S1 are non-basic, and then so on and so forth. So anytime we have a non-zero value, that's going to be a basic variable for that solution, and then anytime we have a 0 value, that's non-basic. So in the next video, we're going to talk about a way we can extend this method. Notice here in the table method, we've only looked at 2 decision variables and 2 constraints, which very much limits the situation. What happens if there are a lot of resources that factor into our situation in terms of optimizing whatever function we have? We need a little bit more of a flexible technique to deal with more complicated situations. So we're going to take the table method, we're going to adapt it a little bit, and we're going to build from there.